the end of our last class, we talked about specific needs for chemical reactions. And we talked about those needs in terms of three different things. The first was reactants, or stuff. Right? We need stuff in order for a reaction to take place. We need to have some stuff to react. The second thing we talked about was collisions. And so in order for that stuff to react, it can't be over here and over here. It has to come together in order for bonds to be broken and bonds to form. And so we need that stuff to collide. Okay? And so assuming we have that stuff comes together and collides, well, sure, that's all well and good. It can collide, but if it just it collides and bounces off, nothing's going to happen. So those collisions have to have some amount of energy to them. And so if they have energy, if they have sufficient energy, then those bonds can break, other bonds can form, and we can have a reaction to occur. So the collisions need energy. So for a reaction to take place, we need stuff. We need that stuff to collide. We need the stuff to collide with enough energy to break bonds and form new ones. But throughout the world, there are lots of different types of reactions. Reactions that occur quickly, reactions that occur slowly. And so if you were to think about different types of reactions, we could think about, if we come over to our screen here, we've got a couple of pictures up. We've got a picture of a stovetop where we have natural gas burning on the stovetop. We know that's combustion, where hydrocarbon reacts with oxygen to form carbon dioxide and water, and that's a fast reaction. It produces lots of energy very, very quickly. And we know that because, well, we can think of hydrogen, we can think of hydrocarbons burning, producing lots of energy. We can think of hydrocarbons exploding. Those are fast reactions. But over on the right, we have our old rusted out car. And that rusted out car didn't get to that point very quickly, did it? It got to a point where it was rusted after probably years of being parked under that tree, where it took lots of time, lots of oxygen interacting with that iron to make that rusted car. And so with that in mind, these reactions that we know we have these needs, where we need stuff for the reaction to occur, these collisions to happen, the sufficient energy, but not all reactions occur at the same rate. And so we're going to talk about things that influence rate as far as these two components of a reaction. And the first one to think about is, well, collisions. If we need collisions to occur, how can we increase the rate of a reaction? Well, we can do that by making more collisions. And so we can get more collisions by increasing the number of molecules and their proximity to each other. And so we're going to call that by increasing the concentration of those reactants. And if we increase that concentration, we can increase the rate. But again, if we have collisions where the molecules that are colliding and the reactants are colliding and they're just bouncing off each other, well, they're not going to react. And so in order to increase the energy of those collisions, in order to get them to react, we can do something like raise the temperature. And so we can increase the energy by increasing temperature, which will again increase the rate. And so these two things, increasing concentration and increasing temperature, will allow us to increase the rate of a reaction. And although both of them will allow us to increase and have effect on rates, we're going to take and look today specifically at how concentration affects rates of reactions in order to see what happens when we have a system of reactants reacting to form products. And to do that, we're going to do a little demonstration. Our demonstration will be sort of a macroscopic view of a reaction occurring, a where reactants form products. And so we're going to start out simple. Our reaction is just going to be reactants react to form products. And if we were to consider the rate of this reaction, the rate, as we said, so our rate is going to be proportional to the concentration of our reactants, where the brackets here just stand for concentration. But having a concentration doesn't specifically mean that every reaction of every type of product or type of reactants at a specific concentration will have the same rate. Rates will occur different. You'll get different rates from different concentrations, but you'll also get them from different reactants. And so for a reaction to occur at a specific rate, we can look at it as proportional to the reactants, but it's also proportional to how those reactants react with each other. And we're going to put a proportionality constant in there for a reaction. We're going to call that KFWD, standing for K forward. We'll come back to why it's K forward in a second. But the basic idea is our reactants will react to form products, and they'll do it with a related in such a way that the rate is related to the amount of reactants and this proportionality constant. And so we can illustrate that with our demonstration up here, where we have some water with some blue food coloring representing our reactants. And we're going to use our beaker here as a transfer beaker to represent the rate constant. So if we have our rate of our reaction is proportional to, well, the amount of reactants, and the rate constant, well, a big rate constant, will allow us to have a reaction that produces products fairly quickly. And so with our big rate constant, we can transfer over, we can have our reactants react quickly, but if we were to compare that to a smaller rate constant, a 150 milliliter beaker instead of a 500 milliliter beaker, we would notice that, well, our smaller rate constant means that, well, we're transferring reactants much more slowly over to the product side. And so we could keep at this for a while. We could make all of our reactants react to produce products. But in chemistry, that doesn't really happen. We tend to also get a reaction called the reverse reaction, which is why I called this K forward in the first place. And the reverse reaction is going to look something like this. I'm going to keep my reactants and products on the same side of my chemical equation. But in this case, we can say, well, because sometimes the products break apart into the reactants. They can decompose, they can react to form products. So we're going to put an arrow in the other direction, saying that, well, products can react to form reactants, and the rate of that occurring, we're going to say, is proportional to, again, in this case, it's the concentration of the products, because the products are the things that are reacting in this case. And so we're going to put our concentration of products in here. And we don't know for sure whether the reaction of the products is going to occur in the same proportions that the reaction of our reactants will occur. So we're going to put a different rate constant in. We're going to call this K reverse. Because those products may react at a different proportional rate than the reactants do to make the products. And so we could illustrate that with our macroscopic system in the same way. If we were to have a similar rate constant to what we had for the reactants forming products, well, then we're going to get a similar rate of transfer of the products back to the reactants. But again, if that rate constant for the reverse reaction is small, then our rate of transfer from the reverse, or from the products to the reactants, is going to be slower in the same way that the rate of change from the reactants to the products was slower when we had a smaller rate constant. Now, there will come a point where these two reactions, the reaction of the reactants to form products and the reaction of the products to form reactants, will have rates that are equal to each other. In other words, we can say that, well, our reactants go to form products but our products also go back and form reactants. And if we were to take these two rates, at some point, depending upon the concentrations of the reactants and products and these two rate constants, we're going to reach a point where the rate of the forward reaction and the rate of the reverse reaction are the same. And so we can say that at that point, K forward times the concentration of the reactants will equal K reverse times the concentration of the products. Okay? And we can look at this as being a reaction in equilibrium, where the reaction of the forward reaction is the same rate as the reverse reaction. And so that would be, we can demonstrate that using our macroscopic view here, where if we were to have two rate constants that were the same, we would get a transfer of reactants and products over the course of time that, assuming they happen at the same time, we're going to get transfers that will, if I don't spill everywhere, will eventually get to a point where the rate of the forward reaction, the rate of the reverse reaction are the same, and the concentrations, or the amount of water, blue water, in these two systems are going to stay approximately the same over time. Okay? However, if one of our rate constants is much smaller than the other, then you can imagine, well, in this case, my rate constant for the reverse reaction is smaller than the rate constant for the forward reaction, and so the rate of the forward reaction will be much faster. But at some point, these two reactions will transfer the same amount of liquid back and forth at the same rate, because they're also not just dependent upon the rate constant, but they're dependent upon the concentration. So at some point, we're going to get, and we're probably pretty close to that point now, where the rate of transfer from the products to the reactants equals the rate of transfer between the reactants and products. And you can see that at that point, we're going to have, although the equilibrium has been reached, where the change in products reactants equals the change from reactants to products, the proportions of the reactants and products are different, and those proportions are going to depend upon the rate constants themselves. And so if we were to reorganize this equation, we could actually say, let's get our rate constants on one side of the equation and get our concentrations of products and reactants on the other side of the equation. And to do that, we just do a little bit of math rearranging. So we'll get K forward divided by K reverse, and that'll equal our concentration of our products over the concentration of our reactants. And we'll call that K, big K, EQ, which is our equilibrium constant for the reaction, when the rate of the forward reaction and the rate of the reverse reaction are the same. So we have no net change in the concentrations of the products and the reactants. And so we're going to look at a couple demos on your computers today that will allow us to see what happens given various starting conditions. Remember, we started with just reactants and formed products, right? And then we started with just products and formed reactants. Well, we're going to use some simulations on the computers today to see what happens when we start with varying types or varying concentrations of both products and reactants. Right? Good?